considered the father of modern rocketry, was the first to successfully launch a liquid-fueled rocket in 1926. This was a pivotal moment, marking the transition from dream to reality. These early rockets were rudimentary compared to the sophisticated machines we have today, but they represented a crucial first step. They paved the way for the rapid advancements in rocket technology that would follow. To understand how rockets work, we must first grasp the fundamental laws of motion. Sir Isaac Newton in the 17th century formulated 3 laws that govern the motion of all objects in the universe. These laws form the bedrock of rocket science. Newton's first law of motion inertia. This law states that an object at rest stays at rest, and an object in motion stays in motion with the same speed and in the same direction unless acted upon by an unbalanced force. Think of a soccer ball lying on the ground. It won't move until someone kicks it. Similarly, a rocket on the launch pad requires a powerful force to overcome its inertia and propel it upwards. Newton's second law of motion involves mass and acceleration. This law describes how the velocity of an object changes when it is subjected to an external force. The greater the mass of the object, the more force it takes to accelerate it. This is crucial in rocketry because rockets need enormous amounts of thrust to overcome their own weight and Earth's gravitational pull. Newton's third law of motion, action and reaction. This law is the most critical to understanding rocket propulsion. It states that for every action, there is an equal and opposite reaction. When a rocket expels hot gas out of its nozzle, the gas in turn exerts an equal and opposite force on the rocket, propelling it forward. Thrust is the driving force behind a rocket's ascent. It is generated by the rocket engine, which burns propellant, fuel, and an oxidizer to produce a high-speed jet of hot gas. Imagine inflating a balloon and then letting it go. The air rushing out of the opening propels the balloon forward. Rockets work on a similar principle, but on a much larger and more powerful scale. The rocket engine ignites the propellant in a combustion chamber, creating extremely high pressure. This high-pressure gas is then directed through a nozzle, a carefully shaped opening at the bottom of the rocket. As the gas is forced through the nozzle, it expands rapidly, converting its thermal energy into kinetic energy. This high-velocity exhaust stream generates thrust, propelling the rocket upwards. The amount of thrust produced depends on the mass flow rate of the exhaust and the exhaust velocity. The faster and heavier the exhaust, the greater the thrust. Rocket scientists carefully design engines and select propellants to maximize thrust and achieve the desired performance for a particular mission. Section 5. Reaching for the Stars, the Evolution of Rocketry. From the early experiments of Goddard to the powerful rockets of today, rocketry has undergone a remarkable evolution. The development of new technologies and materials has led to increasingly sophisticated and capable launch vehicles. One major milestone was the development of the V-2 rocket by Germany during World War II. While the V-2 had a devastating impact as a weapon, it also marked a turning point in rocket technology. After the war, both the United States and the Soviet Union recognized the potential of rockets for space exploration, and thus began the space race. This competition spurred rapid advancements in rocketry, leading to the development of powerful rockets like the American Saturn V and the Soviet Soyuz. The Saturn V, which powered the Apollo missions to the moon, remains the most powerful rocket ever built. Today, private companies like SpaceX are at the forefront of rocketry innovation. SpaceX, founded by Elon Musk, has developed reusable rockets like the Falcon 9 and the Falcon Heavy, significantly reducing the cost of space travel. Section 6. Space Race and Beyond, a Giant Leap for Humankind. The space race between the United States and the Soviet Union during the Cold War captured the imagination of the world. It was a time of intense competition and remarkable achievements. In 1957, the Soviet Union launched Sputnik 1, the first artificial satellite to orbit Earth. This event shocked the United States and ignited the space race. 4 years later, Yuri Gagarin became the first human in space, orbiting Earth aboard Vostok 1. The United States, determined to catch up, poured resources into its space program, culminating in the Apollo 11 mission in 1969. Neil Armstrong's famous words, "That's one small step for man, one giant leap for mankind," marked a pivotal moment in human history. the space race had a profound impact, not only on science and technology, but also on society as a whole. It inspired generations of scientists, engineers, and dreamers. It led to the development of countless technologies that we use today, from satellites that enable communication and navigation to materials used in everyday products. Section 7. Destination Mars and Beyond, the Future of Exploration. Today, space exploration continues to push the boundaries of human ingenuity. Our focus has shifted from the Moon to Mars, with plans to send humans to the Red Planet in the coming decades. NASA, other space agencies, and private companies are all working towards this ambitious goal. Mars represents the next giant leap in space exploration. It's a planet with the potential for past or even present life, and it holds clues to the evolution of our solar system. Establishing a human presence on Mars is a monumental challenge, requiring advancements in life support systems, propulsion technology, and our understanding of human physiology in space. Beyond Mars, the possibilities for exploration are limitless. The icy moons of Jupiter and Saturn, such as Europa and Enceladus, are thought to harbor vast oceans beneath their frozen surfaces, potentially containing life. Exploring these distant worlds will require even more advanced spacecraft and technologies, pushing the boundaries of human innovation. Section 8. The Uncharted Territories of Space Travel. While chemical rockets have taken us to the Moon and beyond, they have limitations. The vast distances between stars and galaxies pose significant challenges for traditional propulsion systems. To reach these distant realms, we need to explore new frontiers in space travel. One concept is nuclear fusion propulsion, which harnesses the immense energy released by fusing atoms together. Fusion rockets could potentially achieve much higher speeds than chemical rockets, significantly reducing travel times. Another concept is antimatter propulsion, which uses the annihilation of matter and antimatter to generate thrust. This highly theoretical technology holds the promise of near light-speed travel, but faces significant technological hurdles. Warp drives, wormholes, and other exotic propulsion systems remain firmly in the realm of science fiction. However, the pursuit of these seemingly impossible technologies often leads to unexpected discoveries and advancements that benefit other fields. Section 9. Inspiring the next generation of explorers. Rocket science and space exploration are not just about building rockets and launching satellites, they're about inspiring future generations to dream big and pursue careers in STEM, science, technology, engineering, and mathematics. When we invest in space exploration, we invest in our future. The discoveries made in space have a ripple effect, leading to advancements in medicine, communications, materials science, and countless other fields. Moreover, the challenges of space exploration foster innovation and creativity, pushing the boundaries of human ingenuity. As we continue to explore the cosmos, we must inspire and educate the next generation of scientists, engineers, and explorers. They will be the ones to push the boundaries even further, unraveling the mysteries of the universe and ensuring that humanity's journey among the stars continues for generations to come.